Today I'm going to be explaining how to find the numerator and denominator of a transfer function for a process that is under PID control. So the last problem we just completed, we did just this. So I'm just going to give a brief summary of how we completed this, and then we're going to move on to our next step. So in our process, we have an H2 set point going in, which leads us to a plus minus controller, which outputs our error signal. Then we go through our PID controller, which outputs our Q1. Our Q1 is our flow 1. And then we're going to go through our first tank. So we have a transfer function of A1 R1S, A1 R1S plus 1 in the denominator over R1. So that's our first tank. This transfer function will output our height 1. We will go through another transfer function of 1 over R1, which will output our Q2. And then we will go through our second tank, which is A2 R2S plus 1 in the denominator over R2. And now this tank will output our variable that we're looking at, which is our H2. And from this tank, our system will also go through a measurement device, which reads our H2 value out in meters. So we're just going to put a 1 in this box to describe that we're already in the unit that we want to be in. And this measurement device will send our H2 value back to our plus minus controller, which will compare our H2 set point and our H2 to give us our error signal. So looking at this problem, we can see that our R1s between these two transfer functions will cancel. So we also know that in transfer functions, generally you use the variable g. So our PID controller is going to be our GC. Our process between our tank 1 and our tank 2 is going to be our GP. And then our measurement device is going to be our GM. So in the last problem, we also found the transfer function for our PID controller, which can be explained as our big P is equal to our KC, or our proportionality constant, times our tau D, tau I, S squared, plus tau I, S plus 1, and this is all divided by tau IS, multiplied by our error signal. And we also found the numerator and the denominator of our transfer function for the entire system to be our numerator in the forwards direction times our denominator in the backward direction, divided by our denominator in the forward direction times our denominator in the backward direction plus our numerator in the forward direction times our numerator in the backwards direction. So if you would like to see how I calculated any of this, please check out the last video that I posted in this playlist right before this one was posted. And it explains in depth how each one of these was calculated. So now we're going to go to Colab to solve the problem we're looking at now. Okay, so now we are going to find the numerical values for our numerator and denominator of our entire feedback loop transfer function. So like I was saying at the whiteboard, we've already done a problem extremely similar to this, so we're just going to use the code that we built for that problem. So I'm going to run through this a little bit and explain what we did before we get started. So we created a function to turn a transfer function into a polynomial, and then we created a function to turn a polynomial into a transfer function, and then we created a function to multiply two transfer functions, and then we created another function to find the transfer function of our PID controller, and we created a function to find the transfer function for our entire feedback loop. So we also used We also used our transfer function from this SciPy signal.transfer function. We used that transfer function to find the transfer function from Q1 to Q2, like I was explaining in that block diagram on the whiteboard. We also found the transfer function from Q2 to H2. And then we used our function to multiply two transfer functions together to multiply our PID controller transfer function and the transfer functions from Q1 to Q2 and from Q2 to H2. And then we used our function that we created to find the entire feedback loop transfer function. So now I am going to make sure that our variables that are given to us in our problem statement are all correct. So our problem statement gives us that A1 is equal to A2 is equal to 1, and that R1 is equal to R2 is equal to 2. And then we have our PID control parameters, and KC is equal to 1, tau I is equal to 0.8, tau D is equal to 0, and our GM is equal to 1. So we can see that our A1, R1, A2, and R2 are all correct. Our KC has the right value, and we are going to change our tau I to 0.8. We are going to change our tau D to 0. And then we can also see in the function that we built that our GM is equal to 1. So now if we rerun all of our cells, we are going to receive the numerical values for our transfer function. So in our numerator, we will have 0.5s plus 0.625, and in our denominator, we're going to have 1s cubed plus 1s squared plus 0.75s plus 0.625. So now we are going to simulate the step response for this transfer function. So we are going to set our transfer function equal to transfer function FB. So we can use this as a variable. And now to take the step function, all we have to do is transfer function underscore FB dot step. And if we shift enter, this will give us two arrays. So our first array is all of our time values for our function, and our second array is our H2 values or our response values. And one thing to note is that these are our H2 derivation values. So now I'm going to set this equal to our t-plot, which is our time values, but we're saying t-plot so we can plot this out, and our H2 values. So now we are going to use t-plot is equal to np.linspace, and we are going to say that we want our plot to go from 0 to 100 seconds, and then we want 500 data points. So to make our plot just a little bit more accurate, inside of our step function, we can tell it that our t is equal to our t-plot. And now we are going to plot this out. So I'm going to come over here and I'm going to grab my make subplots. Our x is going to be equal to t-plot, and our y is going to be equal to our H2. Shift enter and we get this graph. So we can see on our graph that our transfer function starts at our origin or at 0, 0. And we can see that our step response is working since our H2 values are varying up and down. And then eventually after 100 seconds, it looks like we're getting close to a steady state of 1. So we're going to estimate that our H2 values will reach a steady state of 1 eventually. So I am going to change our time values to go from 0 to 150 seconds and see what happens. So we can see that after about 150 seconds later, our function is getting very, very close to reaching a steady state of 1 meter, which means that our H2 will eventually reach a steady state of 1 meter. Okay, so the last part of this problem, we are going to stimulate the response of our forward transfer function with a sine pseudo cosine error input, and then we are going to compare the plots of H2 and our error signal. So for our forward transfer function, the only two variables that we are looking at is our GC and our GP, or the transfer functions of our PID controller and the transfer function of our process. So we're going to start out by using our tsim is equal to np.linspace. And our tsim is going to represent the time of our simulation. So we are going to say that we're going to go from 0 to 50 seconds and that we want 500 data points. And then we can use np cosine, and we are going to use our frequency times our tsim, and this is going to output our error signal in the Laplace domain. And in our problem statement, we are given that our omega is our frequency, and that is equal to 1 radian per second. So now we can use sig.lsim, and we need to give it our forward transfer function, since that's what we're looking at. We need to give it our error signal and the time that we want this to be evaluated at. So if we control enter, this is going to give us 3 arrays. So our first array is all of our times, and then our second array is our H2 derivation values. And our third array all the way down here, we're not going to worry about this in this problem. So we are going to set this sig.lsim equal to an underscore, since we already have our values of tsim from another equation step. And then we are going to set it equal to H2 and another underscore for the array of values that we don't care about. So now we can use this to plot our system. So we are going to copy and paste our figmake subplots down. And we are going to do 2 lines or 2 curves on this same plot. So we want to plot our H2 derivation values. So we are going to do our x is equal to tsim and our y is equal to H2. And this is going to be the output of our system. So we're going to name that our output. And then we also want to graph our error values. So we are going to set our x equal to tsim still, and our y values are going to be our errors, and this is going to be the input of our system. So let's plot this out and let's compare them a little bit. So we can see at the very beginning that our output graph, our first oscillation goes higher than the rest of them, and our second oscillation doesn't go as low as the rest of them. But we don't really need to worry about this, since we are just looking for the overall long-term behavior of our graph. So one other thing to note is that we do have phase lag in this simulation, which means that the highest point on our input graph is around the same as the lowest point on our output graph, and this suggests that we have a phase lag of about 180 degrees. So overall, our system, we can see that our input amplitude goes higher than our output amplitude, which just means that our input to our system has a higher amplitude than the output of our system. Thanks for watching.